Okay, so this morning I talked to you about things that were fairly classic, and that means that they're in my book from 1997, which you can get upstairs or on Amazon. And today I'm going to talk about right now I'm going to talk about some topics that, come on guys, that are actually also discussed in the book, but I'm going to discuss them in ways that are not in the book. They're the post book. So suffix trees and suffix arrays. Suffix trees are really a tremendous, some people consider them a data structure, but I think of them also as just a defining and organizing concept for a lot of different algorithms. And these were invented in suffix trees were invented around 1973 or so, and had a reputation of that nobody other than the person who invented them, which was a guy named Peter Weiner, and then a second person, McCreight, who did a similar thing. They were the only two people who could understand them, and it was just completely not humanly understandable. And I was fortunate when I was on the faculty about that. Oh, it wasn't about that time. In the early 1980s, one of the graduate students, a guy named Josh Cohen, who's now Josh Benelow, I don't know if anybody knows him, works in security, but for his qualifying exam, he was asked to understand one of these. And so I kind of started to understand it from the work that he did. And then later, Esko Yukonen actually came up with a very understandable version. And so after I had written up Weiner's and McCreight's version, Yukonen came out, and I had to throw out those chapters and rewrite it the way Yukonen is. Okay, so with that background, let me just tell you a little bit about what they are and then how they've evolved. So a suffix tree is a way of organizing all the suffixes in a string. So we have this string Mississippi, and this is a suffix tree for it. And what we see is one leaf, for each one of the suffixes of Mississippi. Oh, we're also adding a $sign at the end, and the $sign is always considered to be lexicographically smaller than any of the other characters. So the suffix of this with $sign is, of course, just starting at position 1 is just the whole string itself, MISSISSIPPI, with the $sign. And then the suffix starting, for example, position 2 is ISSI, ISSISSIPP. It doesn't have the nice rhythm. So anyway, but it's this, everything but the first M. And all the other suffixes are in there, 12 of them, including the $sign by itself. And one of the properties that's, what the suffix tree takes advantage of all the commonalities. So the suffixes 5 and 2 both begin with I, and therefore the tree just has a single I here, and then walks down to 5 for the fifth suffix, and also walks down to 2 for the second suffix. So we're encoding in this way all the suffixes, but taking advantage of repetitions in the suffixes. Again, here's SSI is the beginning of suffix 6, but it's also the beginning of suffix 3. And so if you want to think about this naively, you just think of a trie, TRIE, or a tree where you're first putting in suffix 1 and you have all the letters, and then you put in suffix 2. If suffix 2 agreed with suffix 1 for some portion, then it would share that path until the point where they disagreed. Well, suffix 2 actually doesn't. It begins with I. But then you have 3 and 4. But now when you go back to 5, 5 begins with I, which shares a path to 2. And so we go down until it differs. So ISSI is the suffix that begins at position I, 1, 2, 3, 4, on 5. And it's also the one that begins at position 2. Okay? So now there are two things about this, or several things about this that are important. One is that if you look at any node and you look at the first character on the paths out of that node, they're all distinct. Okay, just the way I was describing how we would naively build this, that's an immediate consequence. So if you ever are trying to locate a substring, let's say ISSI in here, there's no ambiguity about what path you would follow. You'd start at the root, and if our substring is ISSI, you follow I, and there's only one edge whose first label is I, and then you'd follow SSI, and you'd end up here. Okay, so given a suffix tree, it's easy then to determine whether a particular pattern is contained in the text that was used to build that suffix tree. And in fact, this is one of the first applications of this, was that the Z algorithm I showed you this morning, in order to find whether a pattern is inside of a text, you have to process both the text and the pattern. Okay? But imagine the context that comes up all the time in computational biology. We have an enormous database of strings, billions of characters, and that's already known and fixed. And now you have a short sequence string, maybe length 200 or whatever you consider to be short, and you want to find where that occurs inside the database. You don't want to do work that's proportional to the size of the database. Okay, you'd like to do work that's just proportional to the size. We had to move to my machine, which is unfortunately going to do this. At some point, it's probably going to bring up paintings that my father did, and I hope nobody's offended. There's some of them that are, everybody's over 18 here, right? Yeah. Okay, so, huh? Yeah, right. Anyway, so we have this, if you have this enormous database and you build a suffix tree for it, that's ahead of time. Then when you have a pattern and you want to know whether the pattern is inside that text, and we're also going to get this thing constantly annoying. That's why I was preferring to use their machine, but it wasn't working. If you have a pattern, you want to know whether it's in the text, you just walk down the suffix tree until you either exhaust the pattern, which says the pattern is in the text, or you have no way to proceed and you haven't exhausted the pattern, then the pattern is not there. Now, if you want to collect all of them, all the occurrences, let's say of ISSI, you walk down ISSI, and at the leaves, you have the places where ISSI occurs. It starts at position 2 and it starts at position 5. Okay? So if you walk down a particular pattern and then you do a depth first traversal to pick up all of the leaves that are beneath that in the leaf labels, you'll find all of the occurrences of that particular pattern as well. And it takes a little bit of analysis, but the time for collecting all of the occurrences is just proportional to the number of them. So you may think, okay, we went to ISSI, but now this suffix tree is huge, and we're going to walk all the way down to the leaves and back and so on. We're doing a lot of wasted work. But actually, every time you branch, because every branching here actually leads to well, every time you think of it this way, every time you branch, you will come to a different leaf. So the traversal time for the subtrees is just proportional to the number of leaves, and therefore to collect all the occurrences is just time proportional to the number of them. So this is one of the first real applications of suffix trees that allows you to find short patterns inside huge but fixed and known ahead of time texts in time proportional to the small pattern, not involving the time for the big text. But of course you have to build the suffix tree first. All right? Now it looks like if this is annoying, but I don't know what to do with it. It looks like if you build the suffix tree for a string of length n, it might take you n squared time. The naive algorithm I just told you about building, where you're going to take each suffix and walk through the tree till it diverges, that's n squared time. That was a naive algorithm. Also, it looks like n squared space, because here's the full string and then portion of another string and so on. Well, it's easy to get rid of the space annoyance. Every string that labels an edge is actually a contiguous substring of the original pattern. So we can encode this just by start position, end position. Okay, so every edge can be just encoded in constant space. Okay, so that makes it plausible that maybe we could actually compute this thing in linear time. Okay, obviously the size of the suffix tree is just proportional to n. As I said, every branch leads to a different leaf. So since we can now encode what's on every edge in just constant space, now we have a order n space object for the suffix tree. But we still don't, how do you compute it faster than n squared? Well, this was the great result of 1973, I think roughly 73, of Viner and then McCreight, is that you can build a suffix tree in linear time proportional to the length of the whole string. And again, as I mentioned this morning, there's nothing faster than that, because you have to touch every character in the input, and only thing faster would be to smell the string instead of actually processing it. Okay, so I'm not going to show you the McCreight algorithm or the Yukonin algorithm or the Viner algorithm, but I'm going to show you a more modern way of building suffix trees that comes through a later device called a suffix array. All right. Okay, so this is just saying some of the things I've been saying implicitly. The label of a path from a root, the root that ends at a node, is the concatenation in order of the substrings labeling the edges of that path. Path label of a node is the label of the path from the root. Yeah. And for a node V in a suffix tree, the string depth of V is the number of characters in V's label. Okay? All right, so I said a suffix tree for S can be built in order S time. And there should be a parenthesis there. Where's Stephen? Okay. We'll achieve this through our discussion of suffix arrays, which will come after I tell you more about suffix trees. So maybe there's a way of just agreeing to this and getting it to go away. Okay, so I said the suffix trees have a huge range of applications, and if you think of them as a data structure, I once told Dick Karp that there's a suffix tree algorithm which takes what had previously been an exponential time computation down to a linear time computation. And he said that's very unusual for a data structure. Usually data structures will take you from some nice polynomial down to a much nicer polynomial. So suffix trees are not just data structures, they're really also organizing principles for how you're going to build an algorithm. So I have a couple of applications here I'll talk about. Actually, I already talked about the application of looking for a small pattern inside of a large text, and that's a very relevant one in computational biology. All pair suffix prefix overlap, that also comes up in, at least in the old days, Pavel's not here yet, of sequence assembly, okay, where you had a lot of reads and you needed to find for each pair of reads, you had to find the how much the maximum, or actually all of the suffixes of one which match a prefix of the other. Okay, so we can just think of this as two strings, and I want to find all the suffixes of one which match exactly. They don't have to be the same length strings even. Match that. Okay. But actually, given what Stephen had asked this morning, so this morning I talked about longest common subsequence, and we did that with dynamic programming. And then Stephen Brenner asked about longest common substring. Okay, so let me do that one instead. I mean, there are probably, I probably know 50, 60 applications, non-trivial applications, and I do want to talk about the Lempel-Zib as well. But let me talk about longest common substring. And Mike talked about that too. Longest common substring of two strings. Don't have to be the same length. So this is alpha and this is alpha. Okay? And so a substring is contiguous. Subsequence can be broken up by spaces or other characters. So we want to find what is the longest string in one sequence, which is also in the other one. Okay? And you can think of naive algorithms, but they certainly wouldn't be linear time. Let's just say they're both the same length. So we want order n. And I believe this is a problem that was conjectured by Knuth. At least one of these classic problems was conjectured by Knuth to not be solvable in linear time. Only n log n time would be possible. But let me just show you how you do this in linear time using a suffix tree. So let's say I build a string which is S1 concatenated with S2, and I'll put something in there just to separate them. Probably really don't need that. And then I build a suffix tree for that S. Okay? And I've told you, I've advertised at least, that we can build suffix trees in linear time. Okay? Now, then we can, just by doing either a bottom-up or a depth-first traversal or whatever. So every leaf here is indexed by its position in S. Okay? So we know which one of these come from S1 and which one of these come from S2. And maybe even there's one that comes from both. Okay? So every leaf we can say because of the dollar sign, anyway, for other reasons. Each one will either be from S1 with a dollar sign or from S2. Okay, let me back up a little bit. We can have generalized suffix trees which encode a set of suffixes even if they're not from the same string. Okay, so we can have all the suffixes from S1 and all the suffixes from S2 encoded in a single suffix tree. Right? Okay, so in that case, every leaf either comes from a suffix that's an S1 or a suffix in S2. And I was just trying to be fancy by concatenating these. Well, let's just say we have that. So we have a suffix tree that represents all the suffixes either they come from S1 or they come from S2. Okay? Now, visually looking at this, what is the longest common substring? It's the longest path where we count what's a path by its string depth. That is, how many characters are on here. It's the longest path, longest string depth of a path down to a node, maybe this branches off, down to some node which is an ancestor of a suffix that comes from S1 and a suffix that comes from S2. Okay? Now you can think it conversely. The longest common substring is a prefix of a suffix. Any substring is a prefix of a suffix. So every substring is a walk from the root down to somewhere. Okay? Partial walk. It doesn't have to come to the leaves. So when we walk down here, this substring is common to both S1 and S2 because there are leaves beneath here that are one that's labeled S1, labeled S2. So all we have to do to find the longest common substring, once we've built the suffix tree for both S1 and S2, is we take a walk, depth first, traversal, whatever, and note when have we bumped in yet. Now I'm going to do this bottom up. Okay. Should never talk about something I haven't prepared. But anyway, bottom up, I'm just going to note whether we've seen an S1 beneath here. Bottom up means from the leaves. So here we've seen an S1. You convey that information to here. Here we've seen an S2. You convey that information to here. Here we've seen, you convey that information upwards. So this is a node that's seen both S1 and S2. So we can label every node with to note whether beneath it there's something from S1 and something from S2. And then we can just do a depth first traversal to find the deepest one of those, the ones with the largest string depth. Okay, so that's how you can do longest common substring in linear time. Obviously, all the work I was just talking about is doable in linear time. Okay, any questions on that? Lots of different applications. So I'm going to talk about Lempel-Ziv compression, which is something very important and widely used. There are several papers about Lempel-Ziv. Sometimes sometimes it's Lempel-Ziv, sometimes it's Ziv-Lempel. And I thought, okay, that's because they're sharing the credit. Sometimes they'll invert it. But then I realized, well, maybe that's just the difference between reading the names in English or reading them in Hebrew. Okay, so I mean, if they actually always were Lempel-Ziv, but you read it that way, then it's Ziv-Lempel. Or I don't know. What's the convention in Hebrew if you have two names? I mean, I know what the convention is if you have numbers. You know, you're reading like this, and you run right to left, and you run to the number 1, 2, 3. You don't call it 3, 2, 1. You jump anyway. Side.
Then I can tell you why. The 76 paper is ordered Lempel and Ziv.
Oh, okay.
But the real papers, 77 and 78, are Ziv and Lempel.
Oh, okay. So it's just anyway. LZ or ZL, you can find them that way. Very important results. Why isn't this switching? Okay. All right. So it's a data compression. It's a string compression method. Okay. So you take a long string and you want to compress it into smaller. Obviously, it has to be invertible. You have to be able to go backwards and get the original string from the compressed one. And the basic idea is, well, this is a little bit of a knockoff of the real idea, but it's close enough to get the gist of it. Is here's this long string that we're trying to compress, and here I have this A, B, A, X, C, A, B, et cetera, et cetera, et cetera. Well, so you start with the letter A because what can you do? I mean, you have nothing to go on. You have to start on the first letter. And then from the next position, you ask, what's the longest substring starting from here that has been seen before in this string? Okay. Well, in this case, there isn't one. It's a B, so you output a B also. Okay. And you move on one position. Then you have, okay, this example isn't going to take us very far, very fast. Then you have AX. Well, A has appeared before, so now you can write down that this character has been seen at starting at position 1, and that substring is of length 1. Okay? So that's great compression. You've just converted one character into 1, 2, 3, 4, 5. Okay. So it doesn't get an advantage until quite a ways away. So let's say we have ABAX. C, okay, so now when you get out to here, ABAXC has been seen before, okay? That does occur, and so instead of writing out any portion of this, you just say, oh, this is starting position 1, and for 5 characters, that's my representation of it. So in this particular little example, I've broken even at that point. Now, in this little example so far, every repeated occurrence or prior occurrence was from the first position. Okay? So we could do that with the Z algorithm, right? The Z algorithm would say from every position, what's the longest substring there that equals a prefix. But we want to do it more generally for any previous. So you have A, B, AX, let's make this really long, okay, and it starts here at position 1001, and then later you have it again, AXYZ, and you're at a point in the Lempel-Ziv compression algorithm where you've compressed everything, you've represented everything up to this point, now you have to represent what's left, and so you ask, what's the longest substring that starts here and has occurred previously in the string that we've processed. And so here we would, if we can find that quickly, we would say 1001, 1, 2, 3, 4, 5, 6, 7. Okay? So we replace 7 characters by 5, or whatever. And you can see this you know, the real advantage comes when the sequences are long and there's a lot of repetition, which there is in DNA, okay, and there is in English. And this is actually the basis for, but one more thing. When you get to a position, if you get to a position where there is none, let's say you have a W, okay, W's never occurred before, then you obviously output W, okay? So here we're having some notation that says the same thing, and the next slide is even worse. Pseudocode, which just basically says do what I just said. You start at I equals 1, and you compute the first position where there's a substring starting at position I, which is equal to the substring that starts at Li, and this is its length Si. And if you actually found one back there, then you just output the starting position and the length. I guess, yeah, this is the length, this is the starting position. And you increment now I plus Li, because you can jump over all of those ones. Okay, this is just notation. Does anybody, let me try to explain it a little bit better. But it's just saying in pseudocode what I was just saying is you're at a position I, and you want, is there a substring that starts at position I which has occurred before, and you want the first occurrence of that, and that would be at Si, and its length is Li. So you would, for here, you would just then output Si, Li, and then skip Li positions to here, and that's when you have to start compressing again or do the same thing. Otherwise, if Li is not bigger than 0, there's no previous occurrence of any pattern that starts at position I, then you just output that particular character, single character, and you move over by 1 position. Everybody get it? Okay, that's the Lempel. That really is, with some little embellishments, the Lempel-Ziv data compression. And there's a lot of engineering on top of that people have done. And so when you read those papers, you get easily swamped by all the data, the engineering, software engineering, and algorithm engineering. But it's really that simple, and it has all kinds of provable properties of coming close to Shannon compression bounds, and it's pretty much optimal. Now in English, this is the basis for, I think, called bzip, which is a Unix utility. In English, it compresses maybe typical down to 1/5 of the size. But in DNA, which is, first of all, shorter, smaller alphabet, and lots of repetitions, I've been told the compression is much greater. I don't know exactly, but. Okay, well, how do we implement this algorithm that I just told you about? It's really simple. You build a suffix tree for S, okay? All right. And then after we've built the suffix tree for S, we're going to process it with a linear time traversal, which will label every node V. Remember, this is there's a string down to V. We're going to label and each one of these is a starting position in S, position in S. And so we're just going to, let's say this is 3, 7, 2, 4. We're just going to label this with the smallest of these, so that's the leftmost occurrence of this string. So we label that with V, with 3, okay? V with 3. So, and again, this is easy processing, just bottom up. What's the smallest number that you've seen beneath it? You label it with that. Okay. So then, as I'm doing the Ziv-Lempel algorithm, the Lempel-Ziv algorithm, we get to a point where I have to compress the rest of these things. And remember, what am I trying to compute here? I'm trying to compute what is the longest substring that starts at I, which has occurred somewhere previously. Okay? Well, so you just go to the root of the suffix tree, and you start walking down this. You start walking down this string that you're seeing in here. Okay? Until you can't proceed any farther. There's the next character over here is not, you're at a place where the next character here is not the next character you would encounter in that walk. Okay? So that has found the longest substring that starts at position I that occurs somewhere previously. And where is it? Well, you might not actually end up at a node. You might end up somewhere in the middle. But where that previous occurrence is written at the first node beneath where you stop, because that was the left, that was the smallest number beneath here, and we've already pre-processed those. And then there's actually one little extra sub-case. What happens if you have overlapping occurrences? That is, you find, so this goes way out, and here's where it begins again, and it goes all the way to here. Okay, so you have to pay attention to that. So you take this number, you take this length, and if that goes too far, then you chop it off. That's it. And what was the time? Well, starting from here, the time was proportional to the length of the substring that you were walking along. I should have mentioned that the alphabet we're dealing with is constant, a constant size. Okay, we have a fixed alphabet, so it has size 256 or something, 1,000, whatever, which means that when you get to a node and it branches multiple ways and you want to follow one that's labeled C, even without any fancy data structures, because this out degree is bounded by the size of the alphabet, it's just constant time to find what edge you should proceed on. And therefore the walk is just time proportional to the length of what you find. Did you have a question?
Yeah, I do. So before you were emphasizing putting the interval where it started and where it ended.
Yeah.
But here you actually have to walk down that to be sure the letters are.
Yeah, right. Right. We're going to walk down that.
Get any advantage.
Yeah, well, it's just that using the interval to the constant size representation of the string on a substring is just so that the whole data structure is within linear space. Because if it wasn't within linear space, then you couldn't build it in linear time. But yes, you actually have to look. So you have to also have you have a copy of the string, and you have to look at those characters. And so that's it. When you're walking down here, you're also making progress in the string. That is, when you found that there's a match there of length I, Li, then I is being incremented by Li. Okay? So you found there's a match here of length Li, and where you next start working again is at the Li plus 1. So it takes you time proportional to Li to do this walk, but then you get to skip over exactly that many characters in the string, and therefore the total work in the algorithm is just linear in the length of the string. So in linear time, using suffix trees, we're able to do the LZ data compression. And again, the key thing that the suffix tree gave you that the Z algorithm did not is the ability to find the longest substring that begins at a position I that occurs somewhere, anywhere in the previous, or actually the first occurrence in the previous, and not just at a prefix. So the Z algorithm gave you that nice prefix information, but it didn't pick up that information. Okay, and this is sort of similar to longest common substring as well. It's a very similar idea. Okay, so that was another, one of many, many, many applications, non-trivial applications of of suffix trees. Okay, suffix arrays came along somewhat about the same time, maybe a little later, and are usually credited to Miller and Myers of Gene Myers fame. Before he was Gene Myers, he did this. And a number of other things too. This is a more compact representation of the suffixes in a string. And people who actually do implementations, which I don't, say that it compresses to about 1/5 the space. Okay? And what is the suffix array for S? It's just a list of the S suffix starting positions ordered lexicographically by the lexicographic ordering of their suffixes. Okay. So here's the suffix tree for Mississippi again. Okay? And lexicographically smallest suffix is just the $sign by itself. So the first entry in the suffix array is 12, representing the start of the lexicographically smallest suffix. Okay? Then the next entry is 11. 11 is, it's I $sign. That's the string. Okay? And I $sign is actually the second smallest, lexicographically smallest substring. Everybody know what I mean by lexicographically? I mean, that's the way you would find things in the dictionary. Okay? It's purely coincidental that this was, well, no, it's not coincidental that the $sign, which is always at the end, is the smallest because it was defined to be smallest. But it's coincidental that the second smallest was just at the end there. Okay, so the third one is at position 8, which is saying that 1, 2, 3, 4, 5, 6, 7, 8, IPPI $sign is the third smallest suffix, lexicographically smallest suffix. Okay? And so the suffix array here is just what I said. It's a list of the suffix starting positions in lexicographic order of the suffixes themselves. Okay? Now, from a suffix tree, you can get the suffix array in linear time, and we can build a suffix tree in linear times. Ergo, we can build a suffix array in linear time. And what's the suffix array? It's just you take the suffix tree and you do a lexicographic depth first search of the suffix tree. Lexicographic means whenever you come to a node and you have to decide which way should you go with the smallest of the characters, the first characters that label those edges. So you're always trying to find the next lexicographically smallest suffix. So here we would, the smallest here is a $sign. Come back to here. Among the ones that we haven't traversed yet, the smallest is an I. Here, down a $sign. And you pick up the leaves as you encounter them. 12, 11, back up to here. Elemental P. Yeah, P comes before S, so your next, no, it doesn't. Wait a minute. Oh, yeah, sorry, yeah, you're right. P comes before S, so you come down here, you pick up 8, and you come back up here, S, down to here, P again comes before S, and you pick up 5, and so on. So a lexicographic depth first traversal of a suffix tree gives you a suffix array. And I find that very, very helpful to keep that picture in mind when we talk about suffix arrays, because we're not actually going to, our algorithms aren't going to use suffix trees. Okay? So, but conceptually, that's what a suffix array is. Okay, now a suffix array is obviously, it's a smaller object than a suffix tree, so it has less, sort of hand waving, has less information in it. But if you have a suffix array and you have another array that's called LCP, which is roughly the same size as the suffix array. Suffix array is of length proportional to the string we're dealing with, and LCP array, which I'll tell you about, is also proportional to it's about the same size. Most of the fancy, fast algorithms, and I said there are, I don't know, maybe there's 100 nice applications, that use suffix trees can be converted to an algorithm that works just on the suffix array plus this LCP array and has the same running time. Sometimes those algorithms are simpler than on suffix trees. Usually they're a little bit more complicated, but so far every one of the nice algorithms, nice linear time results on suffix trees have been doable on suffix arrays. I don't think there's a general theorem that says that's always possible, but well, yes, there is. Because I'll show you that you can always convert a suffix array plus LCP into a suffix tree. Okay, but we want always to do this within just two arrays, one the size of the suffix array and the other one the size of the suffix array. Okay, so that's the constraint. Not a typical kind of constraint in complexity kinds of analysis, algorithm complexity analysis, because there it's just asymptotic. But here we're really trying to be practical. We're saying we don't want to build a suffix tree because suffix trees tend to be about 5 times the size of a suffix array. And so we want all these algorithms to just work on a suffix array and some other array which is the same size. Okay. So as I said, using a suffix tree to build a suffix array defeats the space savings. And so an open problem for about 10 years was to find an algorithm to build a suffix array in linear time, obviously, but only using S and one added array of size S. Okay? And that was open for, well, I say 10 years. Making these slides, I didn't bother to check it. It might even be longer than that. But around 2003, in the same year, three independent solutions were published. It's like one after another. And they really were independent. Nobody knew about the other one. And so I don't know how this happens, but it's certainly not the first time. And the Karkarian, if I remember, it's a Finnish name, if I'm pronouncing it right, and Sanders is the solution that's the most elegant, and I'll try to tell you a little bit about it. I don't have a lot of time, it is so cute, or at least what makes it work compared to what everybody else tried, and I was one of them who tried and failed. So here's a failed attempt. Remember, what is our object? What is our objective? We want to build a suffix array in linear time, because we know that's doable in a suffix tree, and but we don't want to use a suffix tree. We just want to use the string S, obviously, and one other array in this case. Okay. So here's a failed attempt. So you can, let me define a generalized suffix array is basically a suffix array for a strict subset of all the suffixes in S. So remember I said the suffix array is a listing of the positions of the suffixes in the lexicographic order of those suffixes. Well, I can define coming up with a list of, if I'm just interested in the subset of the suffixes, then I can still talk about their lexicographic order and have a list of those, right? Okay, I'll call that a generalized suffix array. Okay, so what you can do is you can take S and divide it into the odd positions. We're going to have the suffix starts at position 1, suffix starts at position 3, 5, 7, and so on. And the suffixes that start at the even positions, okay, 2, 4, 6, 8, and so on. And then recursively find the GSA for those two lists, okay, those two sets of positions. The suffix array for the even positions, the suffix array for the odd positions. And then, and internally, again, their order. I mean, anybody who does merge sort or any of those classic will see that this is going to work. You merge the two GSAs to form a suffix array of the entire string. Well, what does it mean to merge? Let's say I have 3, 7, 1, 5. So this is the suffix array for the odd positions. I just made up these lists, by the way, so don't try to create a string where this actually is. But imagine that this is the list, this is the generalized suffix array for the odd positions of some string, and this is the generalized suffix array for the even positions of some string. And now I want a true suffix array for all of the positions in the string, all the suffixes in the string. Well, this is the lexicographically smallest from the odd positions. This is lexicographically smallest for the even. And now I just need to find out which of those two is actually lexicographically smallest. Right? Is it the one that starts at position 3 or the one that starts at position 6? Well, the obvious way of doing that, so I have have a pen that doesn't work well. I have the suffix that begins at position 3 and the suffix that begins at position 6, and I've got my two fingers, and I go like that until they are agreeing, until they disagree. Okay, and then X is smaller than Y, so this is lexicographically smaller than 3, and so I output 6. Okay, and then I compare the suffix starting at what happened? Did I skip? Okay. And then since 6 was output, now I compare the suffix that begins at 3 with the suffix that begins at 4, and so on. Okay, and you can see just the same way that merge sort works, that the result of merging this way will give us a suffix array of S. Okay. Well, obviously, if you actually do the two-finger approach, how long does it take to merge two suffixes is proportional to the length of their agreement anyway, but in worst case, it's going to be their entire length. And so that merging of two lists is not going to be doable in order n time, even. It's going to be something like n squared. And people tried very, very hard to be clever, find all kinds of clever ways to do merging that would defeat that. And nobody ever succeeded that way, but we all came up with lots of algorithms that have that time bound. I wrote one that was long and Baroque, and it was never published because it was too Baroque. And if it's not Baroque, don't fit. Anyway. So that's where it sat for a while until Karkarian and Sanders and these other ones. And to me, this is a story that I would love it if I met one of them and they said, "Oh, just one day I was taking this long shower and it hit me," because it's just one of those little ideas that if you don't divide the suffixes into odd and even positions, but instead you divide them into those that start at positions 1 or 2 mod 3 versus those that start at position 0 mod 3. Okay, so I mean, one list is going to be the positions 1 and 2 mod 3 and the other is 0 mod 3. So the first list is twice the size of the second list, but you divide them that way. Then you recursively, then the merging is trivial, as I'll show you. Plus, once you have you're going to recursively find the generalized suffix array for the suffixes that start at position 1 and 2 mod 3. Do that recursively, and when you've done that, you can actually find the suffix array for the ones that start at position 0 mod 3 in linear time, once and for all, not recursively. Okay, so so those are the two ideas that I have to tell you about how you get the second generalized suffix array for the ones that start at position 0 mod 3 quickly if you already have the first one, and then secondly how you do the merging, which is really the cute thing that I wish I hit me while taking a shower. So rank of j, that's the position in the generalized suffix array for suffix j. Okay, that's just where it is. Okay, so if I have a generalized suffix array 3, 5, 1, 7. Okay, so the rank of 1 is 3. It's in the third. It's the third smallest. Okay, so that's the only. Hopefully, that's the only notation you have to keep in your head. This stuff can get very tricky. Okay, now if we've already recursively computed the GSA for the first set, the 1 or 2 mod 3 positions, and then we want to compute the GSA for the second set. Those are the 0 mod 3 positions. We can do that in order S time, or the length of the string. That's total time, not recursive. This isn't. You do it once and for all. It's not a recursive type algorithm. Because what you do is for each position I in the second set, those are the ones that are at position 0 mod 3, you form the two symbol string. What that character actually is, and what's the rank of the next character in the string. Since this is 0 mod 3, this is 1 mod 3. Okay, so I plus 1 is in the first general suffix array. So we take that symbol, we take that rank, which is just a number, and that's my two-symbol alphabet, two-symbol string. And then we use radix sort on these strings to get the GSA of the second set. There's some little bookkeeping involved. Let's say this. I don't know what happened there. So, and this is not in any kind of order. This is just sort of random ordering. This is 3, 4, 2, 6, 1, 7, 5, 8. Those are the numbers that are 1 or 2 mod 3. We have a string length 8. And we have the symbol D is in some position, okay? And the next character over is rank 3 in the first generalized suffix array. Okay, so it says it's the third lexicographically smallest string among the strings that begin at position 1 or 2 mod 3. Okay, but I have to need, bookkeeping means I have to know where this D came from in the original string as well. That's something I have to keep. But if I do a radix sort of this, then I'm going to get A1, A4, A5, C7, D2, D3, D8. So it's taking all of the D, just think of it this way. You've got suffixes at position 0 mod 3 that begin with the letter D. And I want those suffixes in lexicographic order. Well, obviously they all begin with D, so the key thing to know is which is lexicographically smaller starting from the next position over. But the next position over is a position which is 1 mod 3, and you already know the ordering there. So, and the rank is what tells you that, and you can just treat that as a number so that when you lexicographically sort these, now you have the lexicographic ordering of all the suffixes that begin at position 0 mod 3. Again, there's some bookkeeping because you have to know where this A came from as opposed to this A came from in the original string S. Okay? But this is just linear time, and so once you get this one, which is going to be done recursively, this one comes in order and time. Well, that's cool. But we have to merge. Okay, so now we have our two. I didn't typeset properly. Now we have our two. What happened to this? Something's missing here, but okay, it's all right. Now we have our two generalized suffix arrays, and I'm almost done here. It's just another, another 2 minutes for this, and that's basically going to be the end of this talk. So we have our generalized suffix array for positions 1 and 2 mod 3, and we have a generalized suffix array for positions 0 mod 3. Okay? And I told you before how you merge two lists. You could just do the two fingers, but that wouldn't be the time we want. Okay? So, but you never compare anything inside here or anything inside here because these are already ordered and these are already ordered. All right, and this is the punchline. This is the really fun thing that they observed. So when I'm doing a comparison, let's say, okay, let's at the very beginning. I should have had I have an example there, but it's not showing up. Yeah, anyway, position 5. So 5 is the suffix that starts at position 5 is the lexicographically smallest suffix that starts at positions 1 or 2 mod 3. And what's a 0 mod 3? 9, okay? Okay, so I'm now looking into here. Here's position 5, here's position 9. I look at these two characters. If they're different, x, y, then I know which is lexicographically smallest. I'm done, okay? One operation. But if they're not, if they're the same, okay, then what do I have to do? I move over. I look at the position 6 and position 10, okay? Well, 6 is still, so this is 1 or 2, mod 3. Okay, now this is 0 mod 3, position 0 mod 3, and this is a position 1 or 5, 1 or 2 mod 3, okay? So again, because they're in different lists, I have to look at these two characters, and maybe if they're different, then fine, we're done again. Whichever of these two is the smallest, we're done. But if they're equal, then I've got to move over. I don't know why I'm erasing that. CW. But what do I move over to? I move over to 11 here, and I move over to 7 here. Okay? 7 and 11. Something about dice. 7 and 11, those are both 1 mod 3. Or 1 or 2 mod 3, sorry, yeah. So this is 1 mod 3. What's 11? 2 mod 3, right? Okay? Everybody get the point? By the third character comparison, you are now in two positions which are in the same list. Okay? 1 and 2 mod 3. So you know their relationship. Remember, you're going to also have things like ranks. So you can just look up what is the rank of 7 in this list and what is the rank of 11 in this list. And now you know which of those two is lexicographically smaller. And so now you know whether the string starting here is lexicographically smaller or larger than the string starting here. So within 3 character comparisons at most, you can determine that. And then that means we decide which one of those two positions we output, which means we can do this merge of the two lists in time proportional to the length of the two lists. So we have the where is this? Suffix Arrays. I'm just trying to find where I wrote down the recurrence relation, the time analysis, somewhere in here. Yeah, okay. So what's the time for this algorithm? Well, you have the positions 1 and 2 mod 3, so that's about 2/3 of S, and you have to find their GSA recursively. So the time to process a string of length S is just one of those. It's a recursive call here on something that's that size, okay? Then, the other generalized suffix array is found in time order S, right? That's what we did. And then the merging is time order S, okay? So you have this recurrence relation, and hopefully that's linear. That solves to order S. Okay. So what haven't I actually told you is the details of how you do the GSA of the first. I just said you do it recursively, but there are some details, and those are pretty standard but quite annoying. And I should have said that so that the real novelty, because all these pieces were all in place when people were trying. The real novelty was recognizing that if I divided up the suffixes in this weird way, the merge would be easy. And that's been generalized in all kinds of different ways you can divide things up. But, oh yeah, so I do have videos for sale outside, and I'll be happy. No, I have videos online, if you look on my website, that I have videos of this entire subject in about an hour and a half, and it has all of the gory details if you want to find out all the pieces. But this is the clever thing here. And do I have any more on this? That is it. Thank you. Oh, but I should say one more thing. I'll do it next lecture. I didn't tell you how to find the LCP, or even what it is. Okay, so I'll do that next time. And then when you have the suffix array and the LCP, you can actually build a suffix tree also. So that gives you the linear time algorithm for building the suffix tree. But I'll fold that into the next lecture because I'm running way over time.